So, hello and welcome everybody to another presentation of Module 2, which covers the field of energy use in public transport. My name is Daniel Hojski. I'm coming from University of Maribor. So today we will explore how the reuse of end-of-life batteries can contribute to circularity in public transport. The first-hand case is the pilot here in Maribor that's been developed within the project CE4CE. Some background to the pilot location. Maribor is the second largest city in Slovenia in terms of both area and population. It has its urban public transport operates through bus lines. The location of the pilot is Spenjača station at Pohorje Hill. And the line that operates there is the G6 line, which is also first fully electric line in Maribor in Slovenia. With regarding super fast charging infrastructure introduced in 2023. In 2025, this year, the new public transport line network has been also introduced in urban public transport, and this means that the G6 line has a 10-minute frequency in peak hours. So 6 buses drives there, different buses drive there in the peak hour. The whole activities in the Maribor and Maribor's PTO in the last decade has been focusing on modernizing the fleet, especially the electrification of fleet. And until 2028, it is already confirmed that the share of electric buses will be more than 50% of all rolling stock. As said, the first e-buses in Maribor arrived up to 10 years ago, and there was an idea of potential need for battery replacement, and the limited and also the limited existing practices also led to develop these ideas of managing end-of-life batteries. So the initial plan was to implement used batteries from Maribor's buses in energy storage for powering buses at the Spenjača station, and main aims was the target was to energy storage to contribute in a mode of 25 kilowatts of power, and also to lower or offload the grid for the same amount. As already mentioned, at Spenjača station there is a super fast opportunity charging system conducted. And in accordance to this, addition to this, also the overnight charging at the depot. The buses that are driving here have LTO batteries of 74 kilowatt hours capacity, so the energy from the overnight charging is not enough for the whole day operation. And this opportunity charging is needed. It is very liable for this line and for these buses. So daily consumption of the line is up to 600 kilowatts hours. Number of charges is up to 45, 50. Here it says 60, as this was taken as a calculation of scenario of the peak hours. Average time of charging is 5 minutes, and energy charged is up to 12 kilowatt hours per charge. And key requirements for energy storage was or are charge and discharge power of 150 kilowatts and possibility of partial charging from energy storage. So here's the situation of the location with all of the objects that has their impact. Here is a pantograph, energy storage, substation, fast charger, and also the location of solar panels in the future, possible location. So for the pilot, the extensive technical feasibility study was conducted, and it covers the following steps, which will be represented in next slides. First was the microlocation, setting the microlocation of the energy storage. There was initially two locations that was taken into account: the location at the fast charger and the location at the substation. The location at the substation was selected, and the challenges within the selection was the feasibility and viability, which shows that both of the solutions was doable and has the same conditions, roughly same conditions. And the second challenge was of a spatial nature, so the aesthetical placement, as the area in front of Spenjača building is very residential. It is many of tourists and people are coming through. So the location at the substation, which is more at the back, was considered as more appropriate. Then the second step was the battery type consideration. In current e-buses and also in Maribor's fleet, there are the most commonly used batteries are the Li-ion types, and within of the Li-ion types there are LFP, NMC, and LTO batteries. LFP batteries are used in older buses and are the least capable of big demand and thermal stability and long life cycle. NMC batteries are more robust, suitable for larger capacities, cost-effective, and widely adopted in modern fleets. And LTO batteries are the newer technology, very robust, allows high charge-discharge rates, has extremely long life cycle, but are very expensive. And in our case of second-hand batteries applications, there are practically no batteries, LTO batteries yet available. So battery acquisition, as inspection of battery health for Maribor was shown that batteries are in a very good shape and that they don't need replacement yet. So market research for batteries was conducted, and batteries was acquired elsewhere. The batteries used in the energy storage are Li-ion NMC. The type is this. We have altogether 2 packs of batteries, together 140 kilowatts hour. Within the acquisition, also an audit was been made of state of capacity and state of health, and it shown that batteries are in very good condition. And also with the batteries came the BMS and battery management system, and the communication protocol were also included. Challenges that arise are that there is no established second-hand market available, and that we can be considered quite lucky to get a checked battery, as the owners often cannot conduct or are not willing to conduct a battery audit. Used batteries are treated as hazardous goods, and the transport needs the ADR certification. ADR means European Agreement Concerning the International Carriage of Dangerous Goods by Road. So also the transport can also be an issue when acquiring second-hand batteries. The next stage was connectivity to grid and charger. We explored 3 principles of integrating energy storage: the serial, parallel, and direct hybrid configuration. And after the research, the parallel hybrid configuration was selected, as it offloads the network. It allows battery storage support ranging from 0 to 100, reducing the power of the network connection, and allows possibility of using electricity from a cheaper tariff. Cons of this configuration are the double conversion and the power losses. But as our charger didn't allow, or there wasn't a possibility to install the direct hybrid configuration, the parallel configuration was selected. Required equipment. So along batteries, there are lots of equipment and works that was needed to be done. This goes for the construction works: container, converters, electrical cabinet, CNC control system, connection cables, cooling, safety sensors, solar power plant, and integration. For the pilot, the 20-feet container was selected. Hybrid 50 kilowatt converter. All the full protection measuring equipment, definition of interface and data access for the control system, the required fire-resistant cables for all the connections. The cooling was air cooling. 3.5 kilowatt plus additional 2 kilowatt for the place air conditioner, and automatic fire and intrusion reporting. And there is also more of a showcase, a small amount of solar power plant on the roof of container included. So here are key components of battery storage in a scheme. We see the air conditioner, temperature, communication control, inverters, fire extinguisher, battery cooling system, and batteries. The next step was the battery and inverter integration, as the batteries in inverters have to be compatible, uh, uh, and this was the parameters that was taken into account: the usage, the battery type, and the voltage range is very important. Also, cooling, but this is not the most important step. Then inputs and connections, and communication protocol, which is very important. So we got the protocol of the second-hand batteries along the batteries, and now plug-in of to convert the protocols, communication protocols may also be required. This is yet to be seen, as we are in the stage of implementation. System operation and performance scenarios. So there we considered several scenarios along with the pilot scenario, also the scenario with contribution of in a range of 50 kilowatts, and also scenario of minimal grid power. So we can see that from the scenarios, the amount of energy contributed varies, and also in spite of this, the C rate is also varying from 0.18 at the pilot scenario to 0.7 at the scenario 3, and maximum is 1C for these non-method batteries. C rate is a measure of how fast a battery is charged or discharged relative to its normal capacity. Here also a cooling requirement can differ, as in other two scenarios. The water cooling is either recommended or necessary. As said, we also included a solar power, solar panels to the pilot to show that also the renewable energy sources are included and can be as a showcase that they can be further integrated. And within the calculations, we conducted two scenarios, one for the roof, container roof, and second one for the full coverage of the line. This would take place to if 335 square meters of solar panels were implemented, and this would mean about around 50,000 of investment cost, but in terms of energy, of the savings of the consumed energy, the whole investment can pay back in several years, like 3 or 4 or 5 years, depends on the detailed characteristics. And in the table below, the characteristics for the Maribor are shown. The panel efficiency was considered 15 to 18. Price 100 to 150 euros per square meter, and the daily irradiance up to averaging 2.7 kilowatts hours per square meters, or in annually 1000 kilowatts hours per square meter. So the calculation was that renewable energy sources, solar panels, with them the energy storage investment can pay back in a reasonable time. On the other hand, only by lowering the network supply power and using the night tariff, there the time of return of investment is much bigger. So this is it from my side. Thank you for your attention.